All right, so we're going to look at some limaçons. We're only looking at the limaçon category, but we're going to look at how they relate to our graphs in our rectangular coordinate system. So if I have this function, r equals 4 plus 4 cosine theta. So we look at the limaçon category. Which one is that? It's a cardioid. Very good. So it's a cardioid. Now, we're going to look first at the equation y equals 4 plus 4 cosine theta. So here's what you got to remember about these two things. These equations look very much alike. When they look very much alike, the graphs look nothing alike, okay? But they are related hugely. And then when the graphs look very similar, the equations are totally different, okay? So we're not going to graph the exact same thing, otherwise it wouldn't be as telling as what it's going to be. So we're going to think first just in the rectangular coordinate system. We know how to graph this, right? We've done this. Cosine graph, we know would start normally like at 1 and come like this, but our amplitude is 4 and we've been shifted up 4. Make sense? So if it's at, my amplitude's 4 and I'm shifted up 4, when I graph that cosine function, it looks like that, between 0 and 2 pi, but then it would just keep going, right? Okay, so if I look at these two together and I think about what is happening here, right? So in the rectangular coordinate system, these are my angles, so they get bigger as I go down the x-axis. This is basically my r values, bigger this way, smaller this way. On the polar coordinate system, these are my angles, they get bigger as I rotate around, and these are my r values right here, okay? So when we graph these together, and we know it's supposed to be a cardioid, so as I'm going, notice how my radius is getting smaller, my r values are getting smaller, my angles are getting bigger, angles are getting bigger. So as I come around, as my rectangular coordinates start to get closer and closer to the x-axis, this is getting closer and closer to r. When I hit the x-axis, I'm sorry, closer and closer to the pole. When I hit the x-axis, I hit the pole. And because I don't intersect through the x-axis, this is going to bounce up off the x-axis and come back up. That's why your cardioid comes into a point, it's going to bounce off the pole and come back around. And as this comes back up, your r values start to get bigger and bigger and bigger again, and that same thing's going to happen over here. R values are getting bigger as the angles are getting bigger, and that's what creates your cardioid. Okay, so there is a relationship there. It is important that you know the relationship, not necessarily right now. In Calculus AB, you're not going to talk about polar at all. BC and Cal 2 is where the polar stuff comes up for calculus. That doesn't mean it doesn't come up in other things, in other maths, in other sciences. So when you're in those and you have to understand the polar stuff deeper than what we are right now, this is one of those connections that you need to be able to make just kind of in your mind, because if you know that this is what's happening, then you know that this is what's happening over here, okay? So I just at least want to expose you to that. So let's look at another one. Let's look at this one, okay? So here, A is greater than B, but does that make this particular one a dimpled limaçon or a convex limaçon? Dimpled, very good. Okay, so again, we're going to start by just looking at the rectangular graph. We know that the parent function for sine looks something like this. But my amplitude is 2 and I'm shifted up 3, so it's going to look like this, right? So as I go through this and I draw my sine function, this one isn't going to bounce off the x-axis. It doesn't even touch the x-axis, right? So the graph is being shifted up off the x-axis or shifted down. It could go either direction. Where the cardioid, where that point of the heart is on the pole, it's going to be pulled away from the pole. That's what makes that dimpled, right? So let's look at these together. So we see, as we start to graph these, this comes around, right? I'm going to come down here. I'm getting close to the x-axis, so I'm getting close to the pole here. But I don't hit the x-axis, so I don't hit the pole, and then I just go back and go back the other way. All right? So since the point of the heart was being pulled away from the pole, the function is being pulled away from the x-axis. Okay, so they are, like I said, related, even though the graphs look totally different. We're graphing the same kind of information, just in a different way. The other thing I wanted you to see with this is, so here this is r equals 3 plus 2 sine theta. This is negative 3 minus 2 sine theta. So if I look at, the only thing that changed were these two signs. This sign, what that does is instead of the function being up here, it will be down here, right? This doesn't change anything. And when you're talking about A and B are positive no matter what. So A is 3, B is 2. They're both positive. So this sign right here tells me whether the sign is up here or down here, but this one isn't going to change what's happening in the function itself, okay, just by the nature of what's happening with it. All right, so now let's look at this one. R equals 4 plus 2 sine theta. So here, A is greater than B again. What kind would this be? Convex, exactly. So when I look here, I have a sine function, amplitude is 2, I'm shifted up 4. When I graph it, should be no shock that it looks something like this. That looks very similar to the last one we just did, right? Because it doesn't touch the x-axis. When I look at these together, the same type of thing is happening as it did with the dimpled, right? Getting closer to the x-axis, I don't actually touch it, and then I go back up. So the dimpled and the convex are related because, again, I'm pulling away from the pole, and the farther this is from the x-axis, the farther this gets from the pole, and the more convex it becomes instead of dimpled. Okay, make sense? So the only one we haven't looked at yet is the one with the inner loop. So what do you think, rectangular-wise, because we got a cosine function, amplitude is 5, vertical shift is 3. What do you think is going to happen with this graph when I graph it that might be different than the other ones? Think of what we did. That first one bounced off the x-axis. These didn't even touch the x-axis. This one, if my amplitude is 5, but I only shift up 3, then I'm going to have to actually pass through the x-axis. Make sense? And that's what's going to create that loop. So that's what this looks like rectangular coordinate system-wise. The one we actually understand, we graphed a ton of these. That should make sense for that cosine function, right? All right, so let's look at them together then. I know this seems like a tedious way to do it, but it's really the only way I can make happen what I want to make happen. All right, so it's cosine. I'm starting up here, which means I'm starting at my maximum R value right here. My radius values get smaller as my angles get bigger. And then when I hit the x-axis, the same thing happens as it did with the cardioid, right? But when I was here with the cardioid, this then bounced off the x-axis and came back up. We're not going to bounce off. We're going to pass through. So since we pass through the pole. While the radius is negative, see, this is what's happening here. Once I get over here, the radius is negative. That's why I start passing through the pole to make these points. While I'm below the x-axis here, I'm on my inner loop. Once I finish that inner loop, I'm back up at the x-axis, and now I'm going to keep going back up here, which means I'm just going to repeat what was on this side. Okay? Make sense? Right now, I want you to see it. I want you to go, oh, okay, that makes sense. I see how they're related. Not going to test you over that. I just want to expose you to it so you understand there is a relationship. They're not two completely different animals that have nothing to do with each other. You're going to think through the rectangular coordinate system a lot when you're doing polar because that's the one that makes more sense to you. That's the one you've been doing for years and years and years. So you have to make sense of this one. But if you know how they're related, then this one that's solidified in your brain and X and Y makes more sense. You can relate it to this and you will know what's happening, what quadrant you're in, all that good kind of stuff. Okay? What questions do we have? Anything? So just a little FYI with that stuff today.